Okay, so we've made another circle, and the book said there was a second way that you could find the center of the circle here.
Yeah.
So what are you going to do here?
First, we're going to start by making two chords on the circle, and chords are a distance from a point to another point on the circle.
Okay.
Yeah.
How do you want to do that?
So we just fold over some distance on the circle.
Alright, I'm looking for a straight edge that you could use to
draw them out.
Draw those in. But the funny thing is we didn't plan ahead, so we need something that can double as a straight edge. It's not really a straight edge. Here we go.
So we have our two chords.
Okay. So why don't we draw those in? Use that as an edge. Get your head back just a little. Alright. So you found these chords by folding.
Yep.
Okay.
Just gonna draw the part that is on the circle.
Alright. Okay, nice.
So that's now we have to find the perpendicular bisectors of each chord.
Okay, how do we do that?
So to find the perpendicular bisector, we fold the vertice of one chord to its other vertice, like that. So this here is the one.
Okay, you can sketch it in, that's fine. Alright, that is the perpendicular bisector of that chord. Okay.
And then do the same thing for the other. And then about here. Looks like it's a little bit off from the actual center.
Alright, well that's fine. It doesn't
Just a little bit.
doesn't have to be perfect. Why does this method also work to find the center?
Well,
So actually first describe the method and then we'll talk about why it works.
well, first we're finding two chords on the
Okay.
circle, any two chords, and then we're drawing their perpendicular bisector and then mapping where they intersect.
Okay. So what do we know here? What do we know about the perpendicular bisector of a chord in a circle?
So the perpendicular bisector is equidistant, that the line is equidistant from the side of the chord.
Okay.
And then if we do that for this, we know that this point is equidistant from the one point is going to be equidistant from the sides, I guess.
Okay.
So there's only one intersection point. I guess if you could do this for like maybe all the chords on the circle, you would probably find that they would all intersect at one point, and then that would be the center.
Okay, yeah, so why? Why, when there's only two, why do they intersect at the center?
So at the center. We know it's equidistant from both chords.
Or tell me about one of the perpendicular bisectors, some of the properties it has besides being equidistant from those 2 points.
Well, that's a right angle.
Yep.
I have all these right angles.
Yep, that's true.
And then it splits the chord in half.
Yep, that's true too. But look at that, look at one of them. Like, let's pick this one that's going up here right now. Can you tell me about that line?
Well, it also sort of looks like a diameter of the circle.
Oh, why might that be a diameter?
Well, the chord, if you rotate it, it's going to be, you can put the chord in a spot where you can slice down and they're going to be perfect symmetry, and that's what we're doing here. We have one half of the chord, so there has to be a half of the circle as well, since it's a right angle.
Okay.
And then if we rotate it, and you can do it for the other chord, it's kind of like the last method. As we're just creating the diameters in a different way.
That's right, you're creating the diameters in a different way. And in particular, the idea that that line is equidistant from these 2 points, we know the middle of the circle is equidistant from those 2 points. Why is that?
Because the middle is just equidistant from all points on the circle.
That's right. So we know it's the same distance away. So that's great. That's a great method for finding the center of a circle. Which one do you think is easier?
I think the folding the circle over is just pretty easy.
Folding the circle over? Okay. All right, cool. Hey, good job, hon.